Right, I'm going to go over some past exam paper questions to do with conservation of energy. Now this is on paper 1 for Edexcel. These questions have been taken from a number of different past papers, and you can see 58 marks over the years have been taken to do with this particular topic. Edexcel call this unit SP3. Right, a wind generator is used as the source of energy for a remote farmhouse. This thing down here. Complete the sentence by putting a cross in the box next to your answer. If the farmhouse is about 7 metres high, the height of the axle of the generator is... Right, so from there to there is 7 metres high. And if we see that's 1, 2, 3, 4, 5, 6, 7. It's about 7 times higher. 7 metres times by 7 is 49 metres. So that's going to be answer B. Complete the flow chart to show the energy transfers that take place from the wind to light a lamp. Okay, so wind has got kinetic energy because the wind's moving. The generator is going to create electrical energy. And then it already tells you the lamp creates the light energy. So 2 marks. Part B. A student produced a diagram to show energy changes in a lamp. So this is a Sankey diagram. So you can see 200 joules of electrical energy goes in, 60 joules of light energy comes out, so that's the useful energy. And you've got some heat energy here, which is wasted. You don't want a lamp to create heat, you want it to create light. Calculate the amount of heat energy produced by the lamp. Okay, so energy in equals energy out. Energy out is going to be the useful energy plus wasted energy. The amount of energy that went in was 200 joules. So far, 60 joules of useful energy. So that means that the wasted energy must be 140 joules. And that wasted energy was, of course, the heat energy. Calculate the efficiency of the lamp. So efficiency equals the useful energy out divided by the total energy in. Useful energy out was 60 joules. Total energy in was 200 joules. So that equals 0.3. If it did want it as a percentage efficiency, you just times it by 100. So that would be 30%. When the lamp is first switched on, it heats up. It then reaches a constant temperature. Explain why the temperature of the lamp remains constant. Right, it just basically means that the heat energy that it's taken in is the same as the heat energy that it's given out. Another way of saying that is that the energy supplied and radiated is at an equal rate. Or an even easier way is that the heat gained equals the heat lost. A wind power system costs £6,000 to install. It saves £250 each year. Calculate the payback time. So the payback time is how long it takes to get your money back compared to the initial cost that you had to pay to install the system. So that's £6,000 divided by £250. So that's 24 years. Question 2. Electricity can be generated using a water turbine. Water gains kinetic energy by falling from the top of a dam. Calculate the minimum height that 7 kilograms of water must fall to gain 1,300 joules of kinetic energy. Right, this might seem like it's a question to do with kinetic energy, but it's not. It's a question to do with gravitational potential energy. If you imagine you've got some water at the top, that water is going to roll down the hill. Now, as it does, the gravitational potential energy that the water has at the top is going to get converted into kinetic energy. So we need to know, how far does that water need to fall? What's the height in order to gain 1,300 joules of kinetic energy? So basically, we need to lose 1,300 joules of gravitational potential energy because it's going to turn into kinetic energy. So gravitational potential energy equals mass times by gravity times by height. So we know that the mass is 7 kilograms of water. We know that the gravitational potential energy that we're going to lose is going to be this amount of kinetic energy that's going to be gained. So if we rearrange this equation, well, let's simplify it first. GPE equals mgh, mass times by gravity times by height. So therefore, the height is going to be the gravitational potential energy divided by the mass times by the gravity, and we'll pop the numbers in. Gravity on Earth is 10 newtons for every kilogram, and that's going to be 18.57 meters. Part 2. As water enters the turbine at the bottom of the dam, the kinetic energy of 8 kilograms of moving water is 1,100 joules. Calculate the speed of the moving water as it enters the turbine. Okay, this time it's about kinetic energy. So write down what you know when you know it. So we know the mass is 8 kilograms. We know the amount of kinetic energy is 1,100. So the equation for kinetic energy is a half mv squared. So if we rearrange that, we need to find the velocity. So you need to make sure that you can rearrange equations. Now we don't want v squared, we want v. So if we square root both sides, that'll just give us v. So if we pop the numbers in, so we want the square root of the kinetic energy divided by a half times by the mass, and that comes out as 16.58 meters per second. Question 3. Moving air can be used to generate electricity using a wind turbine. Figure 8 is a graph of kinetic energy against wind speed for a mass of moving air. Right, so kinetic energy up the side, wind speed along the bottom, and you can see the graph is a curve. Just before the air reaches a wind turbine, it has a wind speed of 15 meters a second. When the air has gone through the turbine, it's got a wind speed of 13 meters a second. As the air moves through the turbine, some of its kinetic energy is transferred to the turbine. Use the graph to determine the percentage of the kinetic energy transferred to the turbine from the air. Right, let's have a closer look at that graph. So what we've basically got is a wind turbine. Now, the wind comes into the turbine and it's at a speed of 15 meters a second. Now, when the wind's gone through the turbine, it's only at 13 meters a second. So in other words, it's lost 2 meters a second. So this wind turbine must be spinning at 2 meters per second. You know what I mean? And it wants to know, determine the percentage of the kinetic energy transferred to the turbine from the air. Right, so we need some kind of way of converting the wind speed into kinetic energy. Well, that's what the graph does for us. So if the wind speed's 15 metres a second, what I would do is I would draw little dotty lines up to your graph like that, and little dotty lines across here like that. Right, what's that? That's about, so hang on, there's 4 and there's 6 and there's 1, 2, 3, 4, there's 5 little squares. So it goes from 4 to 6, so that's an increase of 2, and there's 5 squares. So if we do 2 divided by 5, that means that each increase is 0.4. So each little square is 0.4. Now I reckon that's 1 square, 2 squares, 3 squares. So that's 5.2. So that reading there is 5.2 kilojoules of energy. So when the wind's got 15 metres per second of speed, it's got 5.2 kilojoules of energy. Now, if the wind has got 13 metres per second, so hang on, these axes are horrible. So going from 10 to 15, how many little squares we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so that's an increase of 5, and it's done that in 10 squares. So each square is half a metre a second. And we need to go from 13. So there's 10, that will be 11, 12, 13. So there's 13. So if you draw your little dots going up towards the graph and then come across here like this, that's 4. So that was much easier. So that was 4 metres, so that was 4 kilojoules. Right, so to work out the percentage change, you basically do the change divided by the total and then multiply it by 100%. So how much has it changed by? So it was at 15 metres a second, which was an energy of 5.2 kilojoules. So 5.2 kilojoules. And then when it came out, the wind was 13 metres a second, which is the equivalent of 4 kilojoules of energy. So take away 4 kilojoules. And the total amount that went in was the 5.2, because that's how much it was at the start. And then multiply the whole thing by 100. That's going to be 1.2 kilojoules divided by 5.2 kilojoules multiplied by 100. And that's going to come out as 23%. Now that's a bit of a stinker, that question. It's worth 3 marks, so that means you're supposed to be able to do that in 3 minutes. Now, this is what I mean. If you go into an exam and you've never seen a question like this before, you're never going to be able to do that in 3 minutes. But by practicing to do the questions, like with me going over these papers, you will be able to do it in 3 minutes. So that's the transformational power of purposeful practice. Right, number 4. Which of these is non-renewable source of energy? So non-renewable means you can't replace it. So that's basically going to be the natural gas. Geothermal's renewable, tidal's renewable, and solar is renewable. We were looking for non-renewable. Question 5. Explain why renewable sources provide an increasing fraction of the electricity supply for many countries. Right, well, basically we've found out that non-renewables are polluting the planet with carbon dioxide gas that's creating global warming. So the use of renewable sources is increasing. Question 6. Figure 5 shows a way of projecting a small trolley up a sloping track. When the button is pressed, a spring is released in P that projects the trolley up the track. The trolley travels up the track, stops, and then travels back down. The spring in P always exerts the same force when projecting the trolley. The student investigates how the mass of the trolley affects the maximum vertical height h reached by the trolley. State the measurements the student should make to complete the investigation. You should make use of the equipment shown in figure 5 and any other equipment that's needed. Right, so they've told you everything you need. So they're investigating how the mass of the trolley affects the maximum vertical height. What equipment are we going to use? Right, well, we'll need to measure the mass with a mass top pan balance. And we need to measure the vertical height with a ruler, I'd say. And make sure you say the word vertical. Don't just say how far up the track it goes. That's not what they're doing. They want the vertical height. Now, if that doesn't get us 4 marks, we better add a couple more things. They're trying to work out how the mass affects the vertical height, so we'd better repeat it using a different amount of mass. Figure 6 is a graph of the student's results. Right, that's the vertical height going up the side, and that's the mass of the trolley. The student states that the energy transferred by the spring is the same each time it's used. Use data from any 2 points on the graph in figure 6 to support this statement. Right, what do we know? So they're saying it's the same amount of energy. Right, we've got height, we've got mass, we've got energy, and this thing's going up. So we're basically talking about gravitational potential energy, aren't we? So gravitational potential energy is mass times by gravity times by height. So if we take a couple of different heights and we work out how much energy it's got for that particular height and that particular mass, hopefully, well, if this person's right, they're saying it's just going to be the same energy every time. So we'll be the judge of that. Right, let's pick a couple of values that's easy to measure. So we'll go with 0.18. Again, mark it on the graph. And we'll go with a value of 0.16 for our other value. Right, so how much energy have we got? And the mass of the trolley, right, what's that? So we're going from 0.7 up to 0.8, and there's 10 squares. So each square is just 0.01. So that's going to be 0.7, and then there's 7 little blocks. So that's 0.77 kilograms times that by gravity, which is 10 newtons for every kilogram on Earth, and then multiply that by the corresponding height, which was 0.18 metres. And that equals 1.386 joules. Right, now if this person's right, when I work out the other gravitational potential energy, it should be the same as that. So what have we got? So the mass 0.8, 8, 1, 8, 2, 8, 3, 4, 5, 6. So that's 0.86 kilograms times by gravity, and then times by 0.16 meters. And that equals 1.376. Well, that's not bad. That's pretty close. So I would agree with him. It is the same. And that was using data from any 2 points on the graph. That's what they mean. I've seen this type of question time and time again over the last 24 years. Right, question 7. Before a car brakes, it has kinetic energy. The kinetic energy decreases as it brakes. State what happens to the kinetic energy during braking. Well, Howie, if you're on your bike and you press your brakes, don't the brakes get hot? So basically, the kinetic energy gets transferred into heat energy. Well, where does the heat energy go? Goes to the surroundings. So if it was worth 2 marks, that's what I would say. Dissipates is just a posh word for moves off, if you like. I think I've spelled it wrong, but never mind. Number 8. A cyclist is riding a bicycle at a steady velocity of 12 metres a second. The cyclist and bicycle have a total mass of 68 kilograms. Calculate the kinetic energy of the cyclist and the bicycle. Use the equation, right? Sometimes it doesn't give you the equation, but this time it has. But I would always be writing down what you know when you know it. So we know the velocity, we know the mass, we're looking for the kinetic energy. So even if it didn't give us that, we can identify ourselves, thank you very much, what we've got to work with and what we are trying to work out. So kinetic energy is a half mv squared. We just literally need to bang the numbers in. Remember to square the 12 and do that first as well. So do 12 squared. So 12 times by 12 times by 68 times by a half. That comes out as 4,896. And that'll be joules. Question 9. A student uses a solar-powered battery charger to charge some batteries. The diagram is an energy transfer diagram for a battery being charged. Use words from the box to complete the energy transfer diagram. Right, what we've got. So we've got some energy going in, then it gets turned into electrical energy in the wires, and then it gets energy in the battery. Right. Well, it said that it was solar powered going in, so that must be solar energy going in, or light energy. Remember, we've got to choose from the box. So light energy goes in, and if it's what type of energy is in a battery, well, it's chemical energy. The diagram shows how much energy is usefully transferred by the battery charger. It says it's not the scale. Yeah, remember the thickness of the arrows usually matter, but because it's not the scale, it doesn't matter. All we're interested in is the size of those numbers. Calculate the amount of wasted energy. Right, well, that's your wasted energy there. So energy in equals energy out. We'll put 400 joules in, So far we've got 50 joules out, so that must mean that the wasted must have been the rest, so it must have been 350 joules. Calculate the efficiency of the battery charger. Right, well, the efficiency equals the useful energy out divided by the total energy in. The useful energy out is the energy we get in the battery, so that's the 50 joules. But we had to put 400 joules of light energy in to get 50 joules of chemical energy out. Well, that's not very efficient, is it? 0.125. So remember to get that as a percentage, if it wanted it as a percentage, multiplied by 100. So that's 12.5%. As I said, it's not very efficient. Now you'll notice that's the second time we've had an efficiency question, so that keeps on popping up. We've had a few kinetic energy questions so far, and it looks like now we've got another gravitational potential energy question. Remember, I've took these questions from different papers, so you can see the same questions coming up again and again. So that should give you confidence. Once you learn how to do these questions, there's a good chance that it'll come up again on this year's exam. A ball's got a mass of 0.046, so write down what you know as you know it, so we know the mass M. Calculate the change in gravitational potential energy, so GPE is question mark. That's our target, that's what we're trying to find. When the ball is lifted through a vertical height of 2.05 metres, so we know the height. Now again, it's gave us the equation, but if it didn't, we've got everything we need. We've got gravitational potential energy, mass and height, and you're supposed to know that gravity on Earth is 10 newtons for every kilogram. So if we've got that, and that, it must be this equation here. Right, let's pop the numbers in. And that equals 0.943 joules. The ball is released. Calculate the kinetic energy of the ball when the speed of the ball is 3.5. Now, speed of the ball, we could just say velocity of the ball. So we've got the velocity and we're looking for the kinetic energy. Now, because it's part 2, it's obviously talking about the same ball. So we know the mass is still 0.046 kilograms. Okay, let's just pop the numbers into the calculation. Kinetic energy is a half times by the mass times by the velocity squared. Well, we've saw that a few times now, haven't we? That's a half times by the 0.046 kilograms. Multiply that by 3.5 squared, of course. So make sure you do that first. 3.5 squared times by 0.046 times by a half, and that equals 0.28175. The ball bounces several times. Yep, boing, 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 boing. Figure 4 shows how the height of the ball above the floor changes with time. So that's height above the floor as time's changing. Use figure 4 to estimate the maximum height that the ball reaches after the first bounce. Well, that's the first bounce, and that is the maximum height there. And again, I would mark it on your graph. So it's just below 1. It's in between 0.9 and 1. So I'll say 0.95. Explain why the ball does not bounce back to its starting height of 2.05. Well, that's because when the ball hits the floor, it loses energy as sound, and then even the sound turns into heat. which transfers to the surroundings. It's always the same pattern. I mean, it's only worth 2, but you'd get 3 for that if it was worth 3 next time. Question 11. Figure 14 shows the vertical forces on an aeroplane. So we've got 8.4 kilonewtons going up, and we've got 7.5 kilonewtons going down. The aeroplane is powered by an engine that burns fuel. The fuel supplies a total of 6,500 kilojoules of energy every minute. Right, that sounds important. The efficiency of the engine is 0.7, and it's put as 70% if you'd prefer. Calculate the power output of the engine. Give your answer in kilowatts. Right, so hang on, we're looking for power. So power equals energy transferred per second. Right, power equals energy transferred over time. Right, so first of all, let's just get the power output. Right, well, the efficiency equals the useful energy out divided by the total energy in. Right, let's rearrange that so that we can get the useful energy out. Right, we know the efficiency was 0.7. Now, if you're using the efficiency in a calculation, you need to use just the decimal version, not the percentage. So try to remember that. The total amount of energy in was 6,500 kilojoules. Now it wants the answer in kilowatts. So instead of converting kilojoules into joules, let's just leave it in kilojoules, because then our answer will come out in kilowatts. Right, so the amount of energy you're getting out is 4,550. But that's every minute. Right? Now we need it as power. And power is how much energy you transfer in a second. So we'd better take this value and divide it by 60, because there's 60 seconds in a minute. And that comes out as 75.8. 3 recurring. Explain why the efficiency of the engine is less than 1, so less than 100%. Well, it's always less than 100% because you always lose energy as heat because of friction, and that heat gets lost to the surroundings. Question 12, the last question. Here are some forms of energy. So we've got chemical, elastic potential, electrical, blah, 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 all sorts. Use words from the box to complete the table. Each word may be used once, more than once, or not at all. First one's been done for you. Right, so there's the different devices. Tells us energy transferred from, and energy is most likely transferred into. So if you've got an electric motor, it's electrical energy that goes in and kinetic energy comes out. A bow and arrow, so elastic potential energy in the string. And what happens to the arrow? It moves, so that's kinetic energy. An electric kettle, right, how do you power it? What energy goes in? Electrical. What do you want a kettle to do? You want it to get hot, so heat energy. There you are, heat thermal. Right, and a microphone. What type of energy do you put into a microphone? Well, you talk into it, don't you? So that's sound. Sound energy goes in, and that turns it into electrical energy. I mean, and then the electrical energy gets turned into sound as well. So if they did want to know that, then that's what happens, isn't it? When your voice comes out of the speakers. Part 2. In the electric motor, only some of the electrical energy is transferred into kinetic energy. State what happens to the remaining electrical energy. Well, what does an electric motor do? They're very noisy and they get hot. So it's always the same pattern, isn't it? The energy that gets lost gets turned into heat and sound. And it would dissipate to the surroundings, but it's only worth one, so we'll just leave it there. Part B. Many appliances are sold with an energy efficiency rating. A-rated appliances are the most energy efficient. Here is some information about two types of electric lamp. Right, got a halogen lamp and a compact fluorescent lamp, which gets called a CFL. Right, so you've got 20 joules of electrical energy going in to the halogen lamp, and you get 2 joules of light coming out, which must mean that we've lost 18 joules, wasted. And with the compact fluorescent lamp, oh, look at that, 20 joules has gone in, so it's the same amount that's gone in, but this time 8 joules has came out, which is 4 times more efficient than that one, because that was only 2 joules. And that must mean that we've lost or wasted 12 joules. Right. Calculate how much energy is wasted in 1 second by the compact fluorescent lamp. Oh well, compact fluorescent lamp, how much is wasted? In 1 second, let's just double check that. Yep, in 1 second. So that's 12 joules. Now I've never seen them say how much is wasted in 2 seconds. But if they did, you'd have to say 24 joules, wouldn't you? Just in case, that's 12 joules in 1 second gets wasted. Anyway, just forget about that. Don't want to confuse you. But just be careful. Right, part 2. Use the energy transfer diagrams to explain why the CFL lamp has a better efficiency rating than the halogen lamp. Well, you can base your explanation on a calculation. So efficiency is useful energy out over total energy in. Now, they've both had the same amount of energy going in, 20 and 20, but the compact fluorescent lamp has a lot more. It's got 4 times more useful energy coming out compared to the halogen for that same amount of energy. Part B. The photograph shows an electric heater used to warm garages. When the heater is switched on, it quickly warms up and then stays at a constant temperature. Explain why the heater stays at a constant temperature. Right, look, if something's a constant temperature, it must mean that the amount of heat that it's taken in per second is the same amount that it's losing per second. You know what I mean? Like a human. We're always losing heat, but because of respiration, we're always making heat. So if we are at a steady temperature of 37 degrees C, that's because the amount of heat we are losing is the same as the amount of heat we're making. Right, if you don't like energy in equals energy out, you could say energy gained equals energy lost. And I've saw you get 2 marks for that. But if you don't like that, you could always write it like this instead. And there you go. That's how to take care of business. So I hope that's useful for you. That's 24 years of teaching experience. Nailed it. Right, I'll see you in the next video. Good luck with your exams. Work hard, be nice. Bye for now. Well, I hope the video helped you. Work hard, be nice, and bye for now.